Mars is closer to Earth than any other solid planet you could stand on. It has a day just a little longer than ours, about 24.5 hours. It has seasons. It has polar ice caps. It has canyons deeper than the Grand Canyon and a volcano taller than anything on Earth. If you listen to enough enthusiastic talk, you begin to feel that Mars is practically waiting for us. All that stands between humanity and a neat little colony under a glass dome is better rockets, smarter engineers, and a few $1 trillion. Build a habitat, ship the supplies, pressurize the air, and move in. It sounds reasonable. It sounds like Antarctica with worse weather. But that picture leaves out something essential. The problem with Mars is not that it is far away. The problem is not even that the trip takes months. The real problem is that Mars is trying to kill you in several different ways at the same time. And most of those ways are not engineering problems. They are physics problems. Physics does not negotiate. It does not care how optimistic you are. It simply gives you the consequences of pressure, radiation, temperature, and gravity, whether you like them or not. Let us begin with the most basic requirement for staying alive: air. On Earth, you walk around wrapped in a thick, invisible blanket of atmosphere pressing down on you at about 101 pascals, what we call one atmosphere. Your lungs evolved in it. Your blood chemistry depends on it. Every cell membrane, every fluid balance inside your body assumes that pressure as normal. You do not feel it because you are in equilibrium with it. The pressure outside your body is matched by the pressure inside. Now compare that to Mars. The average surface pressure on Mars is about 600 pascals. 600. That is less than 1% of what surrounds you right now. To experience a similar pressure on Earth, you would have to go roughly 45 kilometers above the surface, far higher than commercial aircraft fly, essentially at the edge of space. That alone should give you pause. But the real danger is not just that the air is thin. It is how thin. There is a critical threshold in aerospace medicine known as the Armstrong limit at around 3 kilopascals, about 6 pascals. Atmospheric pressure becomes so low that water boils at normal human body temperature, 37 degrees Celsius, above that altitude on Earth. If you were exposed without protection, the moisture in your saliva, your tears, and the thin liquid lining inside your lungs would begin to boil, not because you are hot, but because the surrounding pressure is too low to keep water in a liquid state. Mars sits at about 600 pascals. That is roughly 10 times lower than the Armstrong limit. In other words, Mars is not merely inhospitable. It is well below the threshold where your body fluids can remain stable. If you stepped outside on the Martian surface without a pressure suit, you would not simply suffocate in the familiar sense. The moisture on your tongue would begin to vaporize almost instantly. The fluid lining your lungs would start to boil away, impairing gas exchange within seconds. Gas dissolved in your bloodstream would come out of solution, forming bubbles in your tissues, a condition known as ebullism. Your body would swell grotesquely, not explode, but expand as internal gases pushed outward against tissues, no longer held in check by external pressure. You would lose consciousness in perhaps 10 to 15 seconds as oxygen delivery to your brain collapsed. Irreversible damage would follow within minutes. This is not dramatic exaggeration. It is basic thermodynamics applied to the human body. And even if, by some miracle, you could tolerate the pressure, the composition of the Martian atmosphere would finish the job. The air on Mars is about 95% carbon dioxide, roughly 3% nitrogen, a little argon, and only about 13% oxygen. On Earth, the air you breathe is about 21% oxygen. And your body depends not just on the fraction of oxygen, but on its partial pressure. To function normally, humans require an oxygen partial pressure of roughly 16 kilopascals or more. On Mars, the total atmospheric pressure is only 0, 6 kilopascals. Even if it were pure oxygen, which it is not, it would still be far below what your metabolism requires. Instead, you are surrounded by carbon dioxide at concentrations that are not just unhelpful but toxic. On Earth, carbon dioxide levels above about 5% cause headaches, confusion, and rapid breathing. Above 10%, unconsciousness and death follow quickly. 95% carbon dioxide would overwhelm you in moments. Then there is the ultraviolet radiation. Mars has no significant ozone layer because it has almost no free oxygen to generate ozone in the first place. On Earth, the ozone layer absorbs much of the sun's most harmful ultraviolet radiation before it reaches the ground. On Mars, that radiation strikes the surface largely unfiltered. Exposed organic material, including microbes, can be sterilized in minutes under direct sunlight. So even if you could somehow breathe and withstand the pressure, you would still be bathed in radiation far harsher than what you experience here. All of this leads to a simple, brutal conclusion. Mars does not merely lack breathable air. It lacks the physical conditions necessary for your body to remain intact. The pressure is too low to keep your internal fluids stable. The atmosphere contains almost no oxygen and overwhelming carbon dioxide. The ultraviolet radiation is unshielded. The planet is not just empty, it is actively hostile. The difference between standing alive on Earth and dying in seconds on Mars is not technology. It is the quiet, constant presence of a thick, oxygen-rich, properly pressurized atmosphere. And that is something Mars simply does not have. Now suppose you accept that you cannot walk outside on Mars and you retreat into what people casually call a habitat. The word sounds comforting. It suggests a house, a shelter, a place you build and then live in. But on Mars, the habitat is not a house. It is a spacecraft that never moves. Every cubic meter of space you occupy must be artificially pressurized to something close to 1 atmosphere, roughly 100 pascals, while the outside world sits at about 600 pascals. That means every wall, every window, every hatch, every airlock is holding back nearly a full atmosphere of pressure difference at all times. On Earth, if a window seal fails, you get a draft. On Mars, if a seal fails, you get rapid decompression. The air does not politely leak out. It rushes out. The pressure gradient is enormous, and the atmosphere inside will scream through any opening it can find. Depending on the size of the breach, you might have seconds to react. That is not dramatic language. It is simple fluid dynamics. This changes the nature of architecture completely. On Earth, most buildings are designed to handle gravity loads and weather. The internal air pressure is essentially the same as the external pressure, so walls are not constantly fighting an outward force. On Mars, your habitat walls are under continuous tension. Like the skin of an inflated balloon, the larger the structure, the greater the total force trying to tear it apart. A dome 20 meters across, pressurized to near-Earth levels, is holding back millions of newtons of force. Every joint, every weld, every bolt must withstand that load, not for a day or a month, but for years, perhaps decades. If you are talking about permanent settlement, pressure vessels on Earth, abrasive marine, chemical reactors, spacecraft modules are all subject to strict inspection schedules because materials under constant stress develop fatigue. Metals crack, seals degrade, polymers become brittle. On Mars, there is no large maintenance workforce rotating in and out. The same small crew living inside the structure must also monitor, inspect, and repair it continuously. Add to this the extreme temperature swing. At some Martian latitudes, the temperature can vary by 80 to 100 degrees Celsius between day and night. That means your habitat structure is expanding and contracting every single sol, over and over again, year after year. Thermocycling is a well-known cause of material failure. Bridges on Earth require expansion joints. Aircraft are inspected for microcracks caused by repeated pressurization cycles. Pipelines fail from temperature-induced stress. Now imagine your entire living space undergoing daily expansion and contraction while simultaneously holding back nearly a full atmosphere of pressure. Every cycle stresses seals, welds, and structural supports. Microfractures that are harmless at first can grow. A hairline crack in a pressure vessel is not cosmetic. It is a countdown. Then there is the dust. Mars is famous for its dust storms, and not just local whirlwinds. It experiences regional and sometimes global storms that can engulf the entire planet for weeks or months. The atmosphere is thin, so the winds do not have hurricane force in the terrestrial sense, but the dust is extraordinarily fine, on the order of a few micrometers, and highly abrasive. It behaves more like smoke than sand. It infiltrates seams and joints. It coats surfaces. It clogs filters. It scratches transparent materials and reduces the efficiency of solar panels. Over time, this fine dust acts like a slow grinding paste on every exposed exterior surface. A seal that was perfectly airtight on day one may not remain so after years of abrasion combined with thermal stress. On Earth, when building exteriors weather and degrade, you repair them with readily available materials and large crews. On Mars, every spare seal, every replacement panel, every specialized tool must either have been shipped from Earth at enormous cost or manufactured locally in a still fragile industrial system. The comforting image of a colony under glass ignores the fact that what you are really building is a permanently stressed pressure vessel in one of the harshest environments in the solar system. Even the International Space Station, which operates in microgravity without the added complications of dust storms and extreme day-night temperature swings, requires constant maintenance. Components fail, pumps break, modules age, crews rotate, equipment is replaced. No one lives there indefinitely. Now imagine that same level of technical fragility placed on a planetary surface where stepping outside without a suit is lethal and resupply opportunities come only every couple of years. A habitat on Mars is not a static shelter. It is an engineered bubble that must be actively sustained every minute of every day. If the systems falter, if fatigue goes unnoticed, if maintenance slips, the consequences are immediate and unforgiving. Mars does not forgive small mistakes. It amplifies them. Now consider a threat that does not announce itself with explosive decompression or visible storms. Radiation. On Earth, you live beneath two enormous shields that you rarely think about. The first is the magnetic field generated deep within our planet by the motion of molten iron in the outer core. This geodynamo creates a magnetosphere extending tens of thousands of kilometers into space. Charged particles streaming from the sun and from distant cosmic sources are deflected, bent around the planet by magnetic forces long before they ever reach the surface. The second shield is the atmosphere itself. Even particles that slip past the magnetic field must still plow through a thick column of air. That column absorbs, scatters, and attenuates a tremendous amount of incoming radiation by the time what remains reaches the ground. The dose is small enough for complex biological life to tolerate over long time scales. You are protected by a planetary system operating silently and continuously. Mars has neither of these protections in any meaningful sense. Its global magnetic field died billions of years ago when its interior cooled and the dynamo switched off. Without that magnetic barrier, the solar wind, a continuous stream of charged particles from the sun gained direct access to the upper atmosphere. Over hundreds of millions of years, it stripped away molecule after molecule. The atmosphere thinned, surface pressure dropped, liquid water became unstable. The loss of the magnetic field was not just a detail. It was a turning point that reshaped the entire planet. Today, only faint remnant magnetic patches remain in the Martian crust. Fossil traces of the field that once existed. They are localized and weak, offering no global protection. What reaches the surface of Mars is therefore far more intense than what you experience on Earth. Two primary sources dominate. The first is galactic cosmic rays. These are not particles from the sun. They originate in violent astrophysical events, such as supernova explosions and active galactic nuclei scattered across the galaxy. They are mostly high-energy protons, but a small fraction consists of heavy nuclei. Atoms like iron and oxygen stripped of their electrons and accelerated to enormous energies, sometimes approaching a significant fraction of the speed of light. When one of these heavy ions strikes living tissue, it does not gently ionize a molecule or two. It plows a dense track of ionization through cells, breaking DNA strands and causing complex cluster damage that biological repair mechanisms struggle to fix. The second source is solar particle events, bursts of energetic protons released during solar flares and coronal mass ejections. These are typically lower in energy than galactic cosmic rays, but arrive in overwhelming numbers, delivering large doses in short periods. Measurements from instruments on the surface of Mars indicate that an astronaut there would receive on the order of a few tenths of a millisievert per day, adding up to roughly a couple of hundred millisieverts per year. By comparison, the average person on Earth receives only a few millisieverts per year from natural background radiation. That difference is not trivial. Over a multi-year mission, it becomes substantial, approaching or exceeding the career limits currently set for astronauts. And unlike some occupational exposures on Earth, this radiation is not easily avoided. Here is the difficult part. Shielding against radiation is not simply a matter of adding thicker walls. High-energy galactic cosmic rays interact with shielding materials in complicated ways. When they strike dense materials like aluminum, they can fragment, producing cascades of secondary particles, neutrons and lighter ions that may themselves be biologically damaging beyond a certain thickness. Adding more conventional shielding can yield diminishing returns or even worsen the internal radiation environment. Materials rich in hydrogen, such as water or certain polymers, are more effective at slowing and absorbing these particles. But achieving meaningful protection requires substantial thickness, effectively meters of water equivalent. That translates into enormous mass. And mass is the most precious commodity in spaceflight. On Mars, you could bury habitats under several meters of regolith to gain additional shielding. And that is a plausible strategy. But even then, the protection is partial. The radiation environment would remain significantly higher than on Earth. Over time, this increases the statistical risk of cancer, cardiovascular disease, and potentially neurodegenerative effects Studies simulating galactic cosmic ray exposure in laboratory settings have shown persistent cognitive impairments in animal models, including changes in neural structure within brain regions responsible for planning and decision-making. The very organ you depend on most in a remote, high-risk environment becomes vulnerable. Radiation on Mars is therefore not a dramatic, immediate killer like vacuum exposure. It is a chronic, cumulative assault driven by fundamental astrophysical processes. It arises from the absence of a planetary magnetic shield and the thinness of the atmosphere, both consequences of deep physical history. To live on Mars is to accept continuous exposure to an environment that the human body did not evolve to withstand. And unlike a mechanical failure that can be repaired with tools, radiation damage operates at the molecular and cellular level. It is physics acting directly on biology. Relentlessly and without pause, radiation does not simply increase abstract cancer statistics. It reaches into the architecture of the brain itself. Experiments that simulate exposure to high-energy galactic cosmic rays, the same kind of particles that would bombard a crew en route to and living on Mars, have shown structural changes in neurons, particularly in regions associated with executive function. In laboratory animals exposed to doses comparable to those expected on a Mars mission, researchers observed reductions in the density and complexity of dendritic spines in the prefrontal cortex. Those tiny branching structures are where synaptic connections form. They are the physical substrate of memory, judgment, planning, and decision-making. When their structure is altered, cognitive performance changes. Subjects show impaired memory, increased anxiety, difficulty adapting to new situations, and trouble extinguishing fear responses. These are not minor inconveniences. They are degradations of the very capacities you rely on to manage risk, resolve conflict, and respond calmly in emergencies. Now imagine operating a fragile life support system millions of kilometers from Earth while the environment is subtly eroding your ability to think clearly. And radiation is only part of the biological unknown. Mars offers gravity, which at first sounds reassuring. It is not microgravity. Objects fall. You can walk. The acceleration at the surface is about 38% of Earth's gravity. That seems substantial compared to zero. But the critical question is not whether you can stand up. It is whether 38% is enough to sustain long-term human health across years, decades, or generations. We simply do not know. All of our detailed physiological data come from two extremes: full Earth gravity and near weightlessness in orbit. In microgravity, astronauts lose bone density at rates of roughly 1 to 2% per month in weight-bearing bones, unless they exercise aggressively. Muscle mass declines. The heart, relieved of pumping against a strong gravitational gradient, can shrink slightly. Blood redistributes toward the head, contributing to vision problems linked to increased intracranial pressure. The immune system shows signs of dysregulation. Even with rigorous exercise protocols, 2 hours per day of resistance and cardiovascular training. Crews returning from 6-month missions often require assistance upon landing and weeks to months of rehabilitation. Partial gravity sits in a gray zone between these extremes, and that gray zone is largely unexplored. The longest human exposure to reduced gravity outside orbit was on the Moon, where gravity is about 16% of Earth's, and the stays lasted only a few days. That tells us nothing about what happens over years. A systematic look at the available data suggests that gravity levels below roughly 40% of Earth's may be insufficient to fully maintain musculoskeletal and cardiovascular conditioning over the long term. Mars, at 38%, hovers right at or just below that speculative threshold. The implication is unsettling. Even if adults could function reasonably well with intense exercise and medical oversight, what about children? What about pregnancy? No one has studied fetal development in sustained partial gravity. Bone formation, muscle growth, neural wiring, cardiovascular maturation all occur under the influence of mechanical loading. Gravity is not just a background force, it is a developmental signal. Consider a child growing up entirely in 38% gravity. Their bones might mineralize to densities appropriate for that environment. Not for Earth. Their muscles would adapt to lower loading. Their cardiovascular system would tune itself to weaker hydrostatic gradients. If such an individual attempted to visit Earth later in life, they would suddenly face nearly 3 times the gravitational stress they had ever known. Standing might feel like carrying a permanent, heavy backpack. The heart would have to pump against a stronger column of blood. Joints would bear greater forces. There is a real possibility that a generation born and raised on Mars might not be physically capable of returning to Earth at all. This is not an argument against exploration. It is an acknowledgement of ignorance. We do not know how the human body, especially the developing human body, responds to decades in 38% gravity combined with elevated radiation and chronic confinement. Biology evolved under one specific gravitational constant and one specific radiation background. Change those parameters and you enter uncharted territory. The concern is not dramatic collapse on day one. It is gradual divergence from the physiological norms that define our species. Living on Mars would mean conducting a long-term experiment on human development under altered fundamental forces, with the participants unable to step outside the experiment. That is a profound biological gamble, layered on top of every other physical constraint the planet imposes. When people imagine living on Mars, they often picture planting crops in red soil under a transparent dome, as if the ground were simply waiting to be farmed. But Martian soil, more accurately called regolith, is not benign dirt. It is chemically reactive and laced with compounds that pose direct risks to human health. Data from the Viking landers in the 1970s and later, confirmation from the Phoenix mission reveals significant concentrations of perchlorates in the Martian regolith. Perchlorates are salts of perchloric acid and are strong oxidizing agents. On Earth, perchlorate contamination in drinking water is tightly regulated because even at very low concentrations, it can interfere with the thyroid gland's ability to absorb iodine. The thyroid controls metabolic rate, growth, and neurological development. Chronic exposure can lead to hypothyroidism and, in developing children, cognitive impairment. On Mars, these compounds are not trace industrial pollutants. They are part of the native soil chemistry, present at concentrations far higher than what would be considered safe for human exposure. Now combine that chemistry with the physical nature of Martian dust. The particles are extraordinarily fine, often only a few micrometers across, comparable to or smaller than talcum powder. Because the atmosphere is thin and the planet experiences frequent dust storms, including planet-wide events that can last for weeks or months, this dust remains suspended and mobile. It infiltrates every crevice, it clings to suits, equipment, and surfaces through electrostatic effects each time an astronaut returns from outside activities. Dust will be tracked into airlocks and living areas despite the best containment procedures. Inhaled fine particles can lodge deep in the lungs. On Earth, chronic exposure to fine silica or asbestos fibers leads to inflammation, fibrosis, and long-term respiratory disease. While Martian regolith is not identical to those materials, the combination of fine particle size, chemical reactivity, and perchlorate content makes it a serious concern. Living on Mars means living in an environment where the very ground is both chemically and mechanically hostile to your respiratory system. Agriculture, often proposed as a path toward self-sufficiency, therefore becomes far more complicated than simply planting seeds in local soil. Before regolith could be used safely, it would need to be processed to remove or neutralize perchlorates, a step that requires chemical treatment, water, and energy. Alternatively, crops could be grown hydroponically in carefully controlled nutrient solutions using purified water. But hydroponics demands pumps, lighting, climate control, nutrient management systems, and constant monitoring. None of these operate passively. They consume power continuously. And power on Mars is not a background utility you take for granted. It is the central bottleneck around which every other activity revolves. Consider the temperature. The average surface temperature on Mars is around minus 63 degrees Celsius. In some regions, it can drop far lower. Without active heating, your habitat becomes lethally cold. Heating requires energy every hour of every day. Producing breathable oxygen requires energy. Whether you split carbon dioxide molecules, electrolyze water, or maintain plant-based life support systems. Extracting water ice from beneath the surface requires excavation equipment, heating elements to melt the ice, purification systems to remove contaminants, and storage infrastructure to keep it from refreezing. Growing food under greenhouses requires supplemental lighting because Mars receives only about 43% of the sunlight Earth does. Dust accumulation further reduces solar intensity. All of these processes feed into a loop. To grow food, you need water, heat, light, and controlled atmosphere. To provide water and atmosphere, you need power. To generate power, you need infrastructure that itself must be maintained, shielded, and occasionally replaced. Solar panels are an obvious candidate for energy generation, but their output per square meter on Mars is significantly lower than on Earth because of the greater distance from the sun. Add dust, deposition, and periodic global storms that can dim sunlight for extended periods, and solar becomes intermittent and vulnerable. The experience of the Opportunity rover, which functioned for years until a massive dust storm blocked enough sunlight to drain its batteries permanently, illustrates the fragility of solar reliance. Nuclear reactors offer more stable output independent of weather, but they require fuel. Shielding, cooling systems, and highly trained operators. Establishing and sustaining that capability on Mars implies an industrial chain that must either be imported at enormous cost or gradually constructed in situ with limited resources. Every proposed solution returns to the same constraint. Energy is not just another subsystem. It is the enabling condition for all subsystems. Without continuous power, heat fails, air circulation stops, water systems freeze, crops and habitats lose pressure control. On Earth, a regional power outage is disruptive and inconvenient. On Mars, it is existential. The loop is tight and unforgiving. The soil must be processed. The air must be manufactured. The water must be extracted, and the temperature must be regulated, all through machines that require energy. Living on Mars is therefore not a matter of finding a patch of land and adapting. It is a matter of running an uninterrupted, high-precision industrial operation in one of the most energy-constrained environments humans have ever attempted to inhabit. Even if you could solve pressure, radiation, soil chemistry, and energy generation, you still face the tyranny of distance and mass. Earth and Mars are not next-door neighbors in any practical sense. Their relative positions change constantly as they orbit the sun. Efficient launch opportunities occur roughly every 26 months. When the geometry aligns for what is called a Hohmann transfer orbit, miss that window and you wait more than 2 years. When you do launch, the trip takes on the order of 7 to 9 months each way with current propulsion systems. During that time, you are committed. Orbital mechanics does not allow you to simply turn around if something goes wrong. You follow the trajectory dictated by gravity and velocity. If a major system fails 3 months into the journey, the nearest help is not hours away. It is months away, and possibly unreachable. Communication adds another layer of separation. Radio signals travel at the speed of light, and even light takes between 3 and 22 minutes to go from Earth to Mars, depending on their positions. A round-trip exchange can therefore take 6 to 44 minutes. That eliminates real-time conversation. You cannot call a specialist on Earth during a medical emergency and expect immediate guidance. Every crew must be medically self-sufficient, technically self-sufficient, psychologically self-regulating. They must diagnose illness, perform surgery if necessary, repair hardware, debug software, manage crops, maintain reactors, and resolve interpersonal conflict without outside intervention. The delay is not just inconvenient, it changes the structure of decision-making. Autonomy is not optional. It is mandatory. Overlay all of this with the most unforgiving constraint in spaceflight, the rocket equation. Formulated by Konstantin Tsiolkovsky, it relates the change in velocity a rocket can achieve to the exhaust velocity of its propellant and the ratio of its initial mass to its final mass. The crucial feature is the logarithm to gain more velocity or to carry more payload. You need more propellant, but more propellant adds mass, which in turn requires still more propellant to accelerate. The relationship spirals quickly, with chemical rockets delivering even a single kilogram to the Martian surface requires many kilograms of fuel at launch. Each kilogram of cargo represents a cascade of additional mass and cost. Now translate that into daily survival. A human being needs roughly 2,000 calories per day. Even assuming efficient dry rations, that is on the order of half a kilogram of food per day per person. Over a year, that approaches 200 kilograms. Multiply by 10 people, and you are at roughly 2 metric tons of food per year. Before accounting for packaging and waste, add water losses not recoverable by recycling, spare parts, medical supplies, clothing, tools, electronics, and consumables for life support systems. And conservative estimates suggest 1 to 2 metric tons of material per person per year, even with substantial recycling. For a small crew over 2 years between resupply windows, that can mean tens of thousands of kilograms. Every kilogram must be launched from Earth, accelerated out of its gravity well, sent across interplanetary space, and landed safely on Mars. At current launch economics, the cost is staggering. This leads to a stark conclusion. Either a Martian settlement becomes almost entirely self-sufficient, capable of mining, refining, manufacturing, and repairing nearly everything it needs, or it depends on an extremely expensive and vulnerable supply chain stretching millions of kilometers. But building self-sufficiency itself requires shipping heavy industrial equipment in the first place. You must bootstrap an entire industrial ecosystem in an environment that is already hostile and energy constrained. All of this unfolds within profound psychological isolation. A Mars crew is not just physically distant. They are temporally and socially separated from Earth. No quick visits home. No rapid evacuation. No immediate external arbitration in conflicts. The walls of the habitat define the limits of their world. The combination of logistical fragility, mass constraints dictated by the rocket equation, and deep communication delay means that living on Mars is not merely difficult, it is a continuous exercise in operating at the edge of failure, without the safety nets that have always existed beneath human civilization on Earth. After you strip away the romantic language about frontiers and colonies, what remains is a stark distinction between visiting a world and living on one. Humans can probably go to Mars with enough planning, shielding, redundancy, and money. A crew can land, operate for a limited time, and return. Physics allows that. But living there in the way we live on Earth, raising generations, building a self-sustaining civilization, assuming permanence, is something fundamentally different. The word colony implies stability and continuity. It implies that if something goes wrong, life continues anyway. Mars does not offer that margin. On Earth, if a power plant fails, you may lose electricity. You do not lose the ability to breathe. If a government collapses, if supply chains falter, if technology regresses, people still survive because the planet itself remains habitable. The air stays at 1 atmosphere. The oxygen fraction remains near 21%. The magnetic field continues deflecting charged particles. The ozone layer continues filtering ultraviolet radiation. Gravity remains at 1 g. The oceans and atmosphere buffer temperature swing. Nature provides a baseline of survivability beneath every human system. Civilization can weaken or even collapse, and the biosphere still sustains life. On Mars, the situation is inverted. Every breath, every degree of warmth, every glass of water, every calorie of food depends on active, continuous technological intervention. If the power grid fails, the air stops circulating, heaters shut down, water systems freeze, crops and pressure control degrades. The timeline from systems failure to lethal conditions is measured in hours or days, not years. There is no fallback to a benign environment. There is only the raw planetary state. Thin carbon dioxide atmosphere, low pressure, high radiation, extreme cold. A Martian settlement would exist inside an engineered bubble whose integrity must be maintained without interruption across decades. That is a level of fragility our species has never experienced. Understanding why Mars is so hostile reveals something extraordinary about Earth. Every protection that Mars lacks, Earth provides. Our magnetic field exists because the planet is large enough and internally hot enough for molten iron in the outer core to circulate, generating a global magnetosphere. That field has operated for billions of years, shielding the surface from solar and cosmic radiation. Our atmosphere is thick because Earth's gravity is strong enough to retain heavy molecules and because the magnetic field prevented the solar wind from stripping them away. Our ozone layer exists because biological processes over billions of years filled the atmosphere with oxygen, allowing ultraviolet absorbing ozone to form in the stratosphere. Our climate is regulated by an intricate interplay of greenhouse gases, oceans, cloud formation, geological cycles, and living systems that recycle carbon and stabilize temperature within a relatively narrow range. When someone says Mars is our backup plan, they are implicitly suggesting that a collection of machines inside a habitat can replace a planetary scale system built from a molten core 5,000 kilometers across, an atmosphere weighing quadrillions of tons, a magnetosphere stretching tens of thousands of kilometers into space, and a biosphere that has self-regulated for nearly 4 billion years. That comparison is not an argument against exploration. It is an argument for humility. Physics does not bend to optimism. It gives you the consequences of mass, distance, pressure, and radiation. Mars teaches a lesson with uncomfortable clarity. Habitable planets are not the default state of rocky worlds. Change the mass slightly. Alter the internal heat budget. Remove the magnetic shield. Thin the atmosphere. And you do not get a harsher version of Earth. You get a desert where a human being cannot survive unprotected for even a minute. Earth occupies a narrow band of physical parameters where liquid water, breathable air, moderate radiation, and stable gravity coincide. That combination is not guaranteed by any law. It is the outcome of specific initial conditions and long evolutionary histories. There is no simple plan B waiting in the sky. There is one planet in this solar system where you can walk outside without a suit and remain alive. The deeper you understand the physics of Mars, the more remarkable Earth appears. Exploration may expand our reach, but it should also sharpen our appreciation. The most advanced life support system we will ever inhabit is already beneath our feet.